Morning, everyone. I am Iccha Sethi. I'm a principal engineer at Envision, and I'm here to plant a seed in your mind today about how we can use queuing theory in event systems. I know literally everyone here knows what a queue is. It's basically waiting in line, right? We experience it at airports, your lunch line here, your Kanban board if you do it right. So those are all like queues. And queuing theory is the mathematical study of queues. Now, queuing theory has been used in multiple disciplines, to predict things like what's my wait time going to be? Can I predict a delay in the system? Like if you see those boards at the airport, it says your checkpoint 1 is 14 minutes, your checkpoint 2 is like this many minutes. They're all using some form of queuing theory to predict delays. Now, if you look at event systems like Kafka and Kinesis, they're basically streams of data. They're queues. You produce an event, it goes on a partition on a topic, and then the consumer picks up the event in the order it was put on the queue. So first in, first out. FIFO, those are queues. Now, queuing theory has helped other disciplines, and if it can help our event-based systems, we can reduce the number of incidents we have, we can provide better customer experience. So let's see how queuing theory can help us here. Getting a little bit into queuing theory, so you have events arriving, they get on a queue, they're picked up by a service and processed by it, right? Some of the important metrics to consider are, one is lambda, which is arrival rate, the rate at which your events are arriving. You can use different probabilistic models to model your arrival rate. The most common one used is the Poisson process. L is the length of the queue, so that's the number of events waiting to be processed in your queue. And these are some of the time metrics. So W is the time spent waiting in your queue, your waiting time. S is your service time, which is your time spent by your service to process this event. R is your residence time, which is your total time spent in this entire system. Your queue plus your service. So that's basically R is equal to W plus S. There are lots of interesting laws in queuing theory, and based on your probabilistic models of like what model is your arrival rate at or your service rate at, the equations slightly differ, but I'm going to go with the most basic versions of these laws queuing theory offers. One of them is called the Little's Law, which tells you that the total number of events in your system or customers in your system are nothing but your arrival rate times service time. So if you think about it, it's pretty intuitive. Like, okay, events are coming at a certain rate, and it's taking so long to process them. So that kind of tells me how many events are there in my system in total. An even more interesting law is the utilization law. So my utilization law is about how well my service or that system is being utilized. It's nothing but my lambda times S, which is rate of arrival times service time. Now, if you take the inverse of service time, it's service rate. So utilization is arrival rate by service rate. Think about this a little bit. So my numerator is arrival rate at which my events are coming in, and S, service rate, is the rate at which I'm servicing. So if my arrival rate, as it increases, and my service rate stays constant, what is happening is my numerator is increasing. So my system utilization, once it gets beyond 100, your system can't cope with it, and that's a situation you want to avoid. There's a very famous hockey stick in queuing theory, where you have utilization on your x-axis and your residence time on your y-axis. So what this hockey stick tells you is there is a breakpoint in my system where my residence time can exponentially increase. That means events are forever hanging around and not being processed, and it's an unstable system. If you're using concepts like eventual consistency in your architecture, that means it's probably never going to get eventually consistent or take a really long time, and things in your UI are never going to update. It's going to get wonky over there. Yes, I used the word wonky. And we want to prevent this. So, and queuing theory helps you provide graphs like these, laws like these, which can help you, predict how your system's going to behave so that you can allocate more resources and prevent from going on that side of the hockey stick. I'm going to tie this back into a system like Kafka. How do we, apply it? Now, anytime you have a producer producing an event, if you emit a metric, like, event produced, measure that over a given period of time, you have your arrival rate. Now, when you produce an event onto a topic, you produce a timestamp. When your consumer picks it up, subtract the two, and you get your waiting time. Anytime your consumer picks up an event, and you start your timer, when you're done, you stop, you get your service time. The sum of two is residence time. So you have all these metrics readily available to you that you can plot your own utilization versus resident time plot, prevent delays in your system, and don't get paged. So that's my seed in your mind to go think about it. Thank you.